41, and we are representing our sponsoring company, Pratt & Whitney. Our project title is Friction Damping in Riveted and Bolted Connections. The objective in this project was to use a double cantilever beam to study the relationship between bolt preload and its effects of damping upon an oscillatory system. The primary goal is to provide Pratt & Whitney with analytical design iterations rather than testing on physical materials, which will significantly save time and money. A test specimen was provided by the company, and various bolt preloads were compared to riveted joints to aid in developing the required analytical model.
In this project, the method used to find damping is called the half-power method, where Q is the quality factor and it's equal to the frequency at the peak mode divided by the frequency difference at the bandwidth. The damping ratio will be the inverse of the quality factor. Also, it is required to find bolt clamping force, which equals to the torque divided by the nut factor times the bolt diameter.
Our designed adapter mount can be seen on the bottom right corner of Figure 3. It is attached to a modal vibration shaker and is clamping down the double cantilever beam. On the beam, there are 24 riveted joints, which later were replaced with bolted connections. An important point to note are the locations of both accelerometers, one being at the driving end of the shaker and one at the end of the beam. These locations were chosen to allow us to normalize the graphical representation of data and to illustrate a transfer function.
After running many tests, this is the amplitude versus frequency graph generated from a double cantilever beam with riveted connections. For every preload, we ran 3 different tests for 3 different amplitude displacements. Here is the results we found for quality factor and damping coefficients. We got a quality factor range of 24 to 51, and the damping coefficients were less than 1. Therefore, the system isolation was underdamped. This is an amplitude versus frequency graph generated from a double cantilever beam with bolted connections. Due to time purposes, we showed results for only 1 bolt preload. For bolted connections, the quality factor had a range of 40 to 300, which is a much higher quality factor range than the riveted connection. That is due to high preloads on the bolts connecting the double cantilever beam together. In summary, as preload increases, quality factor increases, and the friction between the 2 beam surfaces decreases. Therefore, damping decreases and the system isolation will become underdamped, and this identifies the relationship between preload and damping.
Having the data from testing, we created 2 graphs, one for bolted connections and the other for riveted joints. Each graph has data that has been overlaid to see the effects that different amplitudes have on the motive frequency. Graph 3 representing the bolted connections and graph 4 representing the riveted joints. We concluded that the modes did not vary drastically from one amplitude setting to the other. To validate the data, ANSYS was utilized to verify the modes for the cantilever beam. With a 3.1% difference, we are confident that the data is accurate and precise moving forward to post-processing. After the calculations to obtain the damping coefficients were made, the coefficients were used to produce a damping versus frequency graph shown by graph 5. What can be seen by looking at graph 5 is a damping coefficient being higher for a cantilever beam clamped together by riveted joints versus bolted connections. The riveted joints had a damping coefficient that is more consistent through the given frequency spectrum. Graph 5 suggests that across the tested frequency spectrum, the damping coefficients of the bolted connections drop significantly between the 2nd and the 4th mode, while gradually increasing as more modes were being observed. The 4th mode of frequency holds the biggest discrepancy between the riveted joints and the bolted connections. The team was able to meet the deliverables set by the sponsor, those being acquiring the data for riveted joints and bolted connections, validating that the data obtained is accurate and precise by comparing the calculated modes from ANSYS to the observed modes, and calculating the damping coefficients using the half-power method to finally interpret the data. From a design standpoint, one can choose to use either riveted joints as opposed to bolted connections, as it appears that the effects on damping can be significant.